Hello, welcome ladies and gentlemen. My name is Tim Parsons and I'm moderating the next session. We're together with you, I think, for a little over the next hour. And just to make sure you've taken the right flight, this session is Sector Achievements, Moments of National Pride and Lessons Learned. On that theme of national pride, it's my great pleasure to acknowledge that we are meeting today on the lands of the Waratah people here in Adelaide, and we pay our respects to elders past, present and future. And I'm delighted to have with you some amazing people who are going to share achievements that we have collectively and individually pulled off in the last couple of years, and in fact, some cases, the last few months. And I think one of the only comments I want to make at this stage before we dive into our first presentation is that this preparation for this panel really gave me a sense that we are at the end of the beginning. A lot of people talk about the Australian space sector and the Australian space industry as a nascent sector. It's something that is beginning, it's early stage. It's not yet something that's flourishing and flowering in a scale sense. But in fact, I think we're at the end of that nascency period thanks to some of the milestones and some of the exciting stories that you're going to hear about today. So without that much further ado, it gives me great pleasure to introduce our first speaker, Dr. David Lingard, who is from DSTG. David.
Hello, I'm Dr. David Lingard. I'm the Group Leader for Space Autonomy at DSTG, and I'm also the Mission Manager for the Buccaneer main mission. So I'll take this opportunity to give you an overview of the mission that's currently in orbit. So with the Buccaneer program, there are two missions. We had a Pathfinder mission that launched back in 2017, and that was in partnership with the University of New South Wales, Canberra. And in fact, Craig, he was part of the university team back when we were doing the first Buccaneer mission. And there was a bit of I guess a slower period during the COVID years, but now we're doing the main mission that launched in March this year. So with this main mission, we're incorporating everything that we learnt with the first mission, which was a lot, because that was our first DSTG mission since WRESAT in 1967. Where with the first mission, we used a spacecraft bus from the US, whereas with our current main mission, we're using the spacecraft bus from the local company at Lot 14 Innovor Technologies. We're very grateful for support from Space Command, and this mission stretches back to before Space Command, and so we also acknowledge Air Force as well for their support. And we're very grateful as well for support in launching the satellite. So through a memorandum of understanding with 13 nations for research into responsive space, we're able to get a launch on Transporter 13. And you can see just over on the right-hand side the launch stack. And you might be able to see a little arrow down the bottom pointing to the launch canister for Buccaneer. So we're very grateful to the US Space Test Program for providing that launch for us. And you can see a few images of the satellite there. Obviously a dominant feature is the big cross-shaped antenna that we need at HF at high frequencies from 3 to 45 megahertz. And that leads nicely onto the next slide, which is the payloads. So our key payload is a digital high-frequency receiver. So that allows us to receive HF signals in orbit. And what we're seeking to do is to study the propagation of high-frequency rays through the ionosphere to better understand the ionosphere, because the ionosphere is very important for defence. So I've got a nice little picture there of the payload undergoing vibe testing. So that collection is going really well on orbit at the moment. We're very happy. I haven't got any hard and fast results to show you in this presentation, but there's a lot of processing and analysis, and it's going really well. In terms of our secondary payloads, we've got our laser communications payload, and so demonstrating high bandwidth downlink from space to ground. I think we're almost there now with demonstrating that the ground terminal at DSTG can see the laser in space, very close. We've also got our self-inspection camera called Mantis, and you can see the deployable optic there for capturing self-imagery of the satellite, but it can also capture Earth imagery by rotating that mirror that's deployed out. So we haven't started with that one yet because we want to progress the other two that I've talked about first, and then we'll work with Mantis, but it's not far away. And finally, we have an iridium transceiver on the spacecraft, so we want to be able to demonstrate sending information from the satellite via the commercial iridium constellation down to ground. And that one's proving a little bit more difficult than we expected because we chose a higher altitude for our satellite so that it wouldn't fall out of orbit too quickly, and that actually makes it more difficult to link to the iridium constellation, but we're working through that. In addition, we've got some autonomy experiments. It's called a Scarlet Beta project, working with the SmartSat CRC and collaborating with the University of Sydney, their area for robotics, their Centre for Robotics at the Sydney University. So there what we're seeking to do is to automate the ability of Mantis to capture images, self-images and Earth images. So instead of having an operator detailing out the tasking to capture those images, we'll get the algorithm to do it instead and to manage all of the resources on the spacecraft, such as the battery state of charge and the amount of data that's in storage, get the algorithm to sort that out for us so that there's less human in the loop. So that work is progressing quite well. In fact, the University of Sydney folks are working on that right now in Sydney. So that's going well, and we seek to demonstrate that in the not too distant future as well. So I said that I don't have a lot of, I can't share any hard and fast HF results just yet, but one of the things that we had to do, of course, with the big antenna, we have to stow it into a very small volume for launch, and then when we're in space, deploy it out just step by step. And this is a rather complicated diagram, but what it's showing is that the high-frequency receiver actually has a couple of engineering cameras to image the high-frequency antenna. And we went through 12 stages, just gradually unwinding the high-frequency antenna as it got bigger and bigger, and it went clockwise until eventually at stage 12 in the bottom right, it sprang out into its cross shape. And it was interesting, so we took all those images and we could see the Earth, we could see the sun. Most importantly though, we could see the antenna just slowly unwinding. Some of the stages we couldn't see the antenna because it was out of the field of view, but it was very gratifying that final day when we got the image down and it showed that it had actually sprung into shape. And of course, it only works in microgravity. The big antenna on Earth's surface just goes flop. But in microgravity, it keeps its cross shape. And that's what we're using to receive those signals so that we can better understand propagation through the ionosphere of HF rays. Okay, so that's just a bit of a taste of what we're doing with the Buccaneer main mission currently.
Thank you so much, David. That was tremendous. And I think, audience, we'd love to get your questions at the end of this session. So we're going to have each of the speakers speak, and then we'll have questions at the end. But I'm super intrigued at how you told us that story. We started off with an American spacecraft, and then now we hired an Australian spacecraft. And to me, that is also a sense that we are starting to mature. Would you agree?
No, definitely I would agree with that. So Innovol Technologies are the first commercial supplier in Australia of these small spacecraft buses. And we went through a proper request for tender process in defence, and there was tenders came in from the US and Europe and Australia, and we ended up choosing Innovor. And yeah, I think it's ended up being great for the Australian space ecosystem for sure.
Fantastic, David. Thank you so much. Okay, great pleasure to now invite Patrick Oppel from the Waratah Seed mission up on the stage. Running slightly ahead of schedule.
Yeah. All right. Hi, everyone. I'm Patrick. I'm the Waratah Seed Satellite Systems Engineer. And I've got the honor today to present you an update of what we've done in the last year on our mission, and what were our lessons learned and what we have planned for the future. First, a little bit of a recap for everyone that doesn't know what Waratah Seed is. Waratah Seed was the New South Wales pilot space qualification mission, partially funded by the government of New South Wales, the University of Sydney, and then the payload teams. And there was a big collaboration between all the partners mentioned before, SmartSat CSC, UTS, Macquarie University, and UNSW were part of the big consortium as well. Waratah Seed has 9 payloads on board, and I'm going to go over them quickly before I tell you what we did with them. Firstly, our 2 primary payloads. We have the UTS thermal payload, which is a new type of phase change material heatsink. Those 2 cubes you can see there on the left, they are 3D printed aluminum blocks with some intricate internal structures that decrease the density of the cube, but keep the heat capacity the same. And yeah, those are meant to improve the performance of that in space. And then on the right, we have the GPS receiver from UNSW to demonstrate GPS reflectometry. So we have 2 GPS antennas on board. One is pointing up and one is pointing down and receives the reflected signals from the ocean or ice. Then secondary payloads, we have 7. We have from ourselves, from Quava, we have SPADES or EDDI. It's a plasma wave receiver to detect submillimeter particles and debris hitting the spacecraft, and that creates a plasma cloud. We have 2 payloads that are solar panels from Europa Power and Extraterrestrial Power. Europa Power's solar panels are double junction perovskite cells, while Extraterrestrial send up silicon cells, so they're similar to the ones you have on houses here on Earth. Spiral Blue sent one of their space edge computers for AI into space with us. And then we had Sparrowspace's payload testing contactile tactile sensors. We have Deneb Space's electro-permanent magnetorquer, and Dandelion's biodegradable materials testing experiment. So now a bit of a timeline on everything that has happened in the last year. Since Ivo spoke here, I think pretty much exactly a year ago, when we were in the US to recharge the spacecraft before launch. We launched on the 17th of August, at least Australia time, on Transport 11 together with Canini and Waratah Seed's sister spacecraft Quava 2 that we built at the University of Sydney as well. About 5 hours later, we made contact with the spacecraft for the first time. We were on a call with the Canini team, and that was pretty cool to see that all together. Then the next 2 months, we spent commissioning the spacecraft bus, gaining control of its attitude, and so on. And once we had that, on the 16th of October, we had our S-band commissioning, and that worked on the first try, went very smoothly, and after that, we immediately started with the payload commissioning. By November, we had the first results for our 2 main payloads. That went very smooth as well. And by December, we had actually 7 out of 9 payloads commissioned. And at that time, we were already running operations for the main payloads. So all the payloads that we know that are running already, we're starting to operate them more frequently, and we're still debugging the rest. In February, we had a little bit of a hiccup. Our S-band stopped working. And after a bit of discussions with our supplier and our ground station supplier as well, We determined that it's most likely a heat issue on the S-band radio on the satellite that overheated through too frequent use and just shut itself down. At that point, we didn't know if we would ever speak to Waratah seed again. It was a bit stressful for us, but we were still keeping it running via VHF, UHF. 2 of our experiments we can actually run through the VHF, UHF pipeline. They are connected straight to our OBC, while the other 7 are all on the payload computer, which is connected to the S-band. It took us 5 weeks, but then we got the S-band back up and running, and immediately we were able to prove the 8 out of 9 payloads. That's also where we stand today. The 9th payload, unfortunately, will never run, but everything else was a huge success. We shifted towards payload operations from the end of March. At that point, we had traveled exactly 1 AU in space, so the distance from the Earth to Sun. Today, it's actually, we're about to hit the next milestone, which is the average distance between Earth and Mars, 1.4 AU. And in April, we celebrated a big mission success with all of the payload teams. And since then, yeah, we've been operating the spacecraft, and mostly it's been going very well. We have a couple hiccups with our ground stations here and there, but that's to expect. I want to highlight on the next slide a couple of the results that we were able to achieve for our payload teams. On the left, first is the Matilda payload from UTS, and you can see there the difference their phase change material heatsink makes in prolonging the operational time for the payload or processor. In hindsight, this would be pretty good to have on our S-band radio. Maybe it wouldn't die all the time on us. In the middle, we have the first result from the Harry payload, a GPS track created, the GPS that was measured in orbit, which is also the first time that Andrew Dempster actually got data from one of his payloads. He has sent more than 5 into space in the last 10 years. That's actually the first time we could prove that Harry works. And then on the right, we have the electropermanent magnetoker from the NEP space. And you can see the difference between, on the left, when the normal magnetoker is on, and on the right, when the electropermanent magnetoker is on, how much more torque we're able to produce for the spacecraft. Then a bit about our lessons learned and status. I mean, the mission, as I said, was a great success. We've been in orbit now for 11 months, and we're still going strong, still operating, even though it was only planned to last for 6 months. 8 out of 9 payloads are operational and generate great results for all of our customers. Lessons learned, yeah, the first point, I think that's been iterated often enough, test, test, test. It's been proven very important for us to have an engineering model, not only of our spacecraft, but of all the payloads, and test it before launch, during the operations, all the time, but you can never be sure that if it works on ground, it works on space. We've seen that too. We built a great community of teams with all our payload teams and everybody else in the consortium. We spent multiple weeks with every payload before integration to make sure, firstly, that their design was valid, that it works on ground, that it works with our hardware and software, and then, in space as well. Planning for us was key. We have 9 payloads on board, 9 different missions that we have to plan for. We spend at least 1-2 hours a week always planning the next week ahead. But you can never prepare for everything. You always have to be prepared that not everything goes to plan. Redundancy and resilience, that's more something you learned from Quava 2, the sister spacecraft, that unfortunately had similar issues to what we learned about Canini recently. We had a payload computer died on us in November last year already, and also some other setbacks, all due to radiation. And ground station, that's something that's very topical. We had a couple of hiccups recently, and we would have been a lot less stressed if we just had some backups for that. Then quickly, I want to go over what's next for us at Waratah Seed. We're planning to do a whole series of these spacecraft, focusing on rideshare for research, startups, SMEs, and really design the missions around the payloads as we have done with this first spacecraft. Satellites will be a bit bigger, 12U or 16U, or maybe bigger into the microsat segment, will give us a bit more power, more data, and we want to run at least 1 mission a year in the long term. And at the moment, we're looking for consortium partners, payloads, sponsors, or investors. So if you want to learn more about Waratah Seed the series, please come see me after this, and we can have a chat about it. Or, yeah, also email me or Eva, and yeah. All right. Thank you very much. Get back over to Tim.
Thank you, Patrick. Well done using up that little bit of extra time, and extra points for the ask at the end of your talk. Well done. That was great. Karla from HEO, up next. Isn't this exciting? I feel like we're at such an exciting kind of moment where we're hearing about all these success stories. We're so blessed.
Thanks, Tim. Hi, everyone. It's really exciting to be here today. My name's Karla, and I'm representing HEO. I'm a space mission analyst there. Yes, that's a pretty random job title, but very excited to be talking to you today about what we're up to. So if you haven't heard of us before, we're HEO, and we are on a mission to make space transparent by building technology to image anything in the solar system on demand. That's a pretty big call, and what that looks like at the moment is we are helping defense, intelligence, and commercial companies look at objects in space through what's called non-Earth imaging. This is where satellites in space are taking images of other satellites. So if we're looking at the current state of space, there's a lot of active satellites. The number is, exploding. Launches are happening a lot more often, and adversaries are launching proliferated and advanced constellations. So HEO is building a network of satellites in space and leveraging our proprietary software to provide on-demand, high-frequency data, insights on high-interest space objects for our customers. So we're using images, we're applying AI techniques, and providing those to our customers through our proprietary software, HEO Inspect. So I'm going to talk about a few different use cases and applications that we've started looking into a lot more over the last few years. One of those being launch and early operations, which is a critical time in a satellite's lifetime, and as well de-risking active debris removal and other types of missions that are happening in space. So one thing about resolved imagery is there's a lot of pixels, which means a lot of information to pull. We can see there an image of the EarthCare satellite, which launched last year, an ESA mission. We posted that to LinkedIn, and ESA reached out, and we're very happy to see a picture of their healthy satellite in orbit. And then with our recently developed ConOps, we are now slewing and following satellites as they pass. We do flyby operations. That's how we take our images. And we're able to see tumbling satellites and see that's Landsat 5, a pretty old satellite, and how it is now orbiting in space. And if anyone wants to go up there and take it down, they're going to need to know exactly how it's orbiting and kind of what attitude it's in. Another application is an event last year, a post-debris event and pre the debris event. So Rusas P1, a Russian satellite, it had a massive debris event, and HEO stepped in to kind of help provide information as we had images of it prior to this event. So we are constantly cataloging. Part of my job is looking at what's going on in space, interesting objects, and taking pictures of them constantly. Actually, we've recently passed successful missions at HEO, over 33,000 missions. So yeah, images of Rusas P1, we could see that the solar panels were not properly deployed, and this helps to add to the story of maybe why it failed and there was a debris event. Then we were also able to capture images of the two largest chunks, I guess, of debris after that event and estimate their size and try and help tell the story of, what's going on up in space. So yes, as I said, 3,600, sorry, I was corrected. So yeah, I think a lot of you might have met Will and Haranya. They've been kind of on the space scene for a while, our co-founders. And it's really exciting to see the company grow, and as well the images get better, which is really exciting. So you can see here 3 different images of the International Space Station over time from 2022 to last year. And this is a testament to our suppliers. We're onboarding more as we grow our constellation. We have over 46 sensors, which I'll talk about in the next slide. But yeah, and all of these sensors, these Earth observation providers, didn't know that they could do this type of, technology, but we come in with our software and our knowledge and help them and get really cool images of space objects. Oh, thank you. Sorry. And so yeah, part of that, our mission is to make all of space transparent. So that's not just LEO where we currently are now. We want to get to other orbits, including GEO, cislunar, and I don't know if anyone knows the story of HEO, but it started as an attempt to try and image asteroids. We're going to get back there one day, 2029 maybe. And to do that, we need to get cameras to other places in space. It's interesting, during COVID, the team kind of looked at, everything shut down, how can we build something? And we looked to building something in Australia, which I might talk about in the questions, but we have built 2 NEI specialized cameras, Holmes and Adler, and we now have 7 of our own cameras in orbit on different third-party hosted satellites. So yeah, we had a few launches this year, more coming, and as we head towards IAC, some more announcements hopefully from HEO on who we're going up on as we get to GEO end of 2026. Thank you.
Thank you so much, Karla. And it's true to say, if I'm not mistaken, that some of these are never before taken photographs. Nobody else in the world has been able to take that level of camera. In effect, you're almost competing with governments in terms of the scale that you're operating at. Is that
I
true?
won't say no one else in the world can take images like that, because they can. But yeah, the US have, have been doing this for a long time. And HEO came in as an international commercial company and kind of broke the mold on what non-Earth imagery was, and we're definitely performing best to scale, I would say.
I think you've done a brilliant job educating the market, so congratulations and thanks for your terrific presentation. Now, where's Craig gone? He's disappeared. Oh, there you are. Craig Benson from Skykraft, moving fast. Over to you. A pretty exciting scale story you've got to tell, I believe.
Thanks, Tim. I'm Craig Benson, co-founder, Chief Innovation Officer, Company Director at Skykraft. So our mission at Skykraft, when we first formed the company about 2017, we were looking around for the right kind of mission to do, something that actually was useful, that we could actually secure revenue from long term so we could be commercially viable. We could defend our market position, all this sort of stuff. And we, in effect, came across the air traffic management market where a subsidiary of Iridium had been set up to use some space weight and power they had available on the Iridium Next constellation to do ADS-B, so monitoring aircraft from space to work out where they are over the oceans and other remote areas. And the industry wasn't entirely happy with the service that they were going to provide and the commercial terms and so on. So yeah, there was a niche where we went, we could kind of do this ADS-B thing. The problem was we knew that we could be more cost effective than Iridium Next, so than Arion as the company is now. But the problem was going to be they were going to have a stranded asset in orbit. Okay, and so as Chief Innovation Officer, my job in effect is to make sure that we do things that are commercially viable and technically possible. And that nexus is actually quite hard to achieve sometimes. So it took me about 2 weeks, a lot longer than it should have, to work out that if they were going to have a stranded asset, that also meant they couldn't upgrade it. So what we need to do is do a service that you can't just do from an ADS-B payload. And so we very quickly worked out that the industry was quite responsive to the idea of doing VHF from space. So what VHF is the press-to-talk radio that the pilot and the air traffic controller use when they leave Adelaide Airport, just over here. And the problem with that is it only works when you're within range of land or within range of a VHF transceiver, so it's a strictly line-of-sight type system. And then as soon as you get out beyond that, you're falling back to the HF radio, so the frequency bands that Buccaneer was looking at, shortwave as your grandfather or great-grandfather would have called it, and SATCOM. Okay, and these are not necessarily standard fit items on all aircraft. So we kind of went, okay, let's do this VHF from space. The industry was very receptive, and so we provide direct control of the pilot communication in remote and oceanic areas. The advantage is you don't need to change the aircraft. Okay, aircraft come off the production line at Airbus or Boeing, and in general, the front of the plane, so that everything in front of the door into the cockpit, doesn't get touched for the rest of the aircraft's life. Okay, so by the time the aircraft retires after about 25 years, it's flying avionics that are 20 to 25 years old that were possibly designed 50 years ago. Okay, they're really, really outdated. Now it works, it's fit for purpose, but the problem is they can't update those. It costs a lot of money. There is no incentive for the airlines to upgrade that. So what we do is basically reverse engineer the space segment to actually fit the user segment. And so we support that VHF communication with high quality ADS-B surveillance. What we have is a redundant LEO constellation to do this. What we have designed and are in the process of building is a redundant LEO constellation. The idea being that each individual satellite is allowed to fail and there is no interruption to the service experienced by the pilot or the air traffic controller. So this is not just that you replace the satellite within minutes, you replace the satellite within milliseconds, so there's no interruption to the voice. Okay, so complete continuity of service. So what we're achieving here is reliability through redundancy. The entire company has always been about providing affordable scale for a global constellation. Okay, it's very easy to build a global constellation that's not affordable. It's very easy to build a satellite that doesn't scale to a global constellation. Finding the two is actually really quite challenging. So we've got rapid capability, growth and resilience because it's a LEO constellation, and you're generally refreshing this constellation every 5 years with designs that are realistically only about 12 months out of date by the time you launch them. Okay, so very different to the GEO world. And at the moment, what we've managed to do is get to a point where we're now 12 months from demand to orbit. So what that means is we decide we want more satellites, we start placing orders for parts, and 12 months later they can be on orbit, already being launched on a SpaceX rocket. So this is all about achievements, and I call it boasting. I don't like boasting, but sort of reflecting on where we've been. So our achievements from 2023, so it took us about 5-6 years to get from the point of view of starting the company to actually launching our first payload. But that payload was 300 kilograms. So when we say payload, what we mean is a stack of satellites. It's the rocket provider's payload, it's our satellites. So our first stack of satellites, 5 satellites, 300 kilograms. And this in one fell swoop more than doubled the mass of Australian-built satellites ever launched. Okay, so before January 2023, Australia had built and had launched into space on anyone's rocket, anywhere in the world, less than 300 kilograms worth of satellite mass. Okay, everything bigger than that had been built overseas and launched on behalf of, like, Optus or, that sort of thing. So we then followed that up again with another launch in June 2023 and then used those to do some industry influencing demonstrations to show that you could do VHF from space. And the aviation industry then lobbied, and in December 2023, the International Telecommunications Union changed the rules so that you could actually do VHF from space. Before that, the rules for the International Telecommunications Union said that VHF in that frequency band was a terrestrial service only. It had nothing to do with space. So we got that rule change through. And very soon we have our third launch, so in the next couple of weeks, it'll launch on the NASA Traces mission as a rideshare, and that will then be another 300 kilograms. Okay, so in effect, in just over 2.5 years, we will have launched 3 times the mass that Australia had launched in total before 2023. And of course, you've got other companies, Space Machines have done another 300 kilograms. There's been a bunch of CubeSat missions and so on that are thickening up Australia's capability in space. So these are really good things to reflect upon. We are actually in a different era to what we were even during COVID and the bushfires and all this sort of stuff, right? The world has changed dramatically in that sort of 3 to 5 year period. Okay, in terms of what Australian space is about. And Tim's quite right about his Churchill quote that it's the end of the beginning. So our plan, again, in late 2026 is to scale that to a whole constellation, and that is 50 to 100 satellites on orbit, spread out, doing complete coverage. When we say global, it won't do the North and South Pole, because at the moment we don't have the customer demand to justify putting satellites there, but a mid-inclination orbit providing complete coverage all the way around the world to where 95% of the aircraft traffic is. So finishing off is celebrating the Australian industry, so looking beyond Skykraft and what we've done, because I'd much rather talk about the industry. Australia actually has a very large number of talented people. We are not short of talent in Australia. The key point being we have a bunch of people that have space experience, and we have a very much larger pool of people that don't, and the two of those together are actually all you need. Most of our engineers, scientists, other things like that at Skykraft have never worked in space before they worked at Skykraft. Yeah, Doug, Simon, I think that's about it, of the people that actually have space experience. Okay, the rest of us didn't know how to spell satellite before we started. Okay, I still sometimes spell it wrong. We've got sufficient manufacturing capability. Okay, at Skykraft, our favourite manufacturers, and we don't tend to manufacture our own parts, we design them and then shop them out. Our favourite manufacturers have 5 staff and 3 blue heeler dogs. Okay. Now, not all of them look like that. The pick-and-place machines and so on, there's no dogs in the factory, but the machining and that sort of stuff gets done at really salt-of-the-earth, blue-collar manufacturing places. Generally, we're their only space company that they deal with. Okay. Aside from that, it's standard. They're building trailers, they're building parts for factories and so on. They're not space manufacturers. They don't have a big Australian flag on the wall and a big white epoxy factory. Being small in Australia actually makes for greater trust. Okay, Skykraft, we're in Canberra. Canberra's an even smaller place than Adelaide, and generally you know almost everybody that you deal with on a daily basis, which means that nobody cheats. Everybody does what they say and looks after each other, because you're looking at not just this deal, but the deal after that and the deal after that again. This is not necessarily true in some of the larger economies of the world. Okay, we also don't have to do everything. Okay, the global economy is global. Okay, this doesn't mean that we have to have a cottage industry version of every part of the space industry in Australia just so we can move forward. Yeah. Now, this doesn't mean that it's better to do it overseas, not at all. Okay, but it also doesn't mean we have to bring along a B grade or C grade capability just to have something in that niche. Yeah, we are actually a niche player. If the industry you're in relies on massive scale and cheap or ready access to launch and test facilities, then you probably should relocate to the US or China. Okay. If you are, on the other hand, being smart and you own your own market niche and you dominate that niche, there's no great problem in being in Australia. When you need to, you just jump on a plane to Los Angeles to get that one or two things that Australia doesn't do. It's okay. Most of what you need is actually in Australia. Okay? It's more important to play with the right player and to get really good quality service than it is to have a local provider. Yeah, local providers are good. We like them. They have a natural advantage, but it doesn't have to be. You don't have to do everything. So to sum up then, to go after those market niches, you have to think different. Okay? I might be an ex-Air Force officer, and I managed to masquerade as a very successful one for 12 years, or so I'll claim. Certainly I managed to fool the posting and promotion people. But the insight is that I actually think very different to most people. Okay? So I'll steal the Apple slogan of we need to think different. Okay? What this means is you identify market niches and opportunities that other people in the world haven't done. Okay? And we then have to act differently, which means you have to actually have the courage to stand out, to wear your weird shoes, other things that you might do, irrespective of what other people think about you. Okay? Have the courage to go after your convictions and act differently and seize those markets. Okay? I've finished with a saying that other people have had that I quite like, which is that everybody laughs at me because I'm different, and I laugh at them because they're all the same. Okay? So we can move forward. Thank you.
I think that's a quote that could be attributed to Coco Chanel as well, Craig, so you're in good company. Fantastic. Well, hopefully you're getting lots of ideas for powerful questions. I will reflect on Skykraft's fantastic raise last year, which gave us all huge hope as an infrastructure providing business. So we'll hopefully have a chance to chat to you a bit more about that amazing achievement, Craig. Herve. G'day. Talking about companies that are doing things very differently. Take it away.
For sure. And also saying that 6 years ago I was not in space industry, so we can all do it. Welcome everybody. My name is Herve Astier. I'm the CEO of Neumann Space. If you don't know us, our DNA is in space, propulsion, moving satellites in orbit, and sustainability. And I'm going to talk to you about our story and the achievement and how proud I am of what we have done. We say everywhere we go, without propulsion, there is no space economy. Space economy today is about $600 billion US. It's set to triple within 10 years. The workers of the space economy are the satellites today. We're sending more and more to orbit, and Skykraft is just one example. They are also the guardians, like defense, rely on satellite for a lot of things that they do in space. However, we do have a problem with propulsion. What do we need to move satellite? I have a few examples there. And propulsion has been around for a number of years, but propulsion systems are known to know very complex systems. So we are looking for simplicity in that market. Why they are complex, what they do is one thing, but operational complexity is something difficult. How do you actually manage a propulsion system in orbit? What decision you need to do? All the sensors you need on the propulsion system, everything like that. Safety is also an issue with fuel, for example, for propellant of satellites. Procurement, the conflict in Ukraine has led to a shortage in xenon gas, which is a of propellant for propulsion systems. So price of xenon, for example, went from $2,000 a kilo before the war to $57,000 a kilo. So you can imagine the impact it has if you're using xenon as propellant. Number of things like that. I'm sure our Skykraft will say yes to that, but same thing, when you're building a constellation, you want to launch them quickly and replenish those. You don't want to have to wait a year for your propulsion system or risk issues in your supply chain. So we're looking for simplicity all over. And this is what we're offering. We're offering a different type of propulsion system. I won't talk too much about it, but we're using solid metal as propellants, so no tanks, no pipes, no complex system. Like, it works a bit like an arc welder in space. So it's not a new technology, it's used on the ground. What's novel is to actually use it in orbit. So it makes the system very simple, safe, reliable, and also cost effective. And a few years ago, or maybe 2 years ago, we only had the first one. Now we're developing a portfolio of different propulsion systems. But I'm not here to sell it, although if you want to buy one, just come and talk to me. But I'm here to tell you about the story, what we have done. Started with University of Sydney, where Paddy Neumann is here. He's a big, huge brain, he's a scientist. Came up with this idea. And his idea was he was using vacuum deposition system and measuring speed of particle. And he was looking at particles moving at 20 kilometers a second. And he's a nerd. And he was like, this is faster than orbital velocity. That may be used as a propulsion system. I can do this with metal. I can use space debris as propellant. So he was putting this together. That's why I was talking about the DNA being in space propulsion and sustainability to help the number of satellites in orbit and removing them and using what's already there. So that was University of Sydney about 10 years ago. 10 years ago, that was before we had a space agency. So kind of good luck to try to do anything developing space companies at that point. Paddy then moved to Brampton, western suburbs of Adelaide, in a garage, again, before space agency, just a few of us here, 2 vacuum chambers, a little bit of testing, very, very early. Again, not the right way to do that. What came next, around 2018, 2019, was space agency and a number of other things. One is a good example of strategic alignment between state and federal government was Lot 14. So if you don't know about Lot 14, that's all hospital sites in Adelaide that the government transformed into, I guess, an incubation center for a number of different types of startup in different industries. So moved in there, started to grow the team. We spent about 5 years there, and very quickly it became quite full. Like you have the equipment in the same room, you have the engineers, so it's okay for a while. It's not the best. So, but a good example of what can be done. So where we are today now is we moved out. I think we graduated from Lot 14 in a sense, and we're now in Canton. And what we have today is 3 systems in orbit. Actually, one was with Skykraft here. One is Innovor that we talked about before. One is a company in Denmark. We're launching number 4 in November with SSTL in the UK and a defense satellite. And so building that flight heritage, any space company, that's critical. That's your step number 1 to do something. That's a major achievement already when you get there. But then when you want to deliver, you need to do 2 other things. You need to build the capability to deliver. So you need to build your equipment, clean room, test equipment, commissioning equipment, so we can do all this and manufacture units. And of course, you need to put a customer in front of that. So you need to close that triangle, I guess, between flight heritage, assembly integration and test capability, and the customer. And if you have that, then you can start doing some cool stuff. So this is where we are today, and just very recently, and we'll announce it probably a bit formally at ISE, if we can, is we secured the first constellation as customer. So certainly for us, it's one achievement after the other. The capabilities just from a few months ago, and production has started just 2 weeks ago. So, major change for us. So we are here to talk also about lesson learned. That's the history of the company on one chart. So don't read it, that's not the point. But a few points in there is, it takes time. I think Skykraft is also saying, it took 6 years, I think, something like that. It's the same kind of thing here since we have the space agency. Takes a lot of money, of course. So if you want to build a space hardware company, get ready for that. Lots of testing. And I have the logo of the space agency here. I can add the logo of the state government here and a few other people that help us along the way. So that's how you go from a vision to hardware commercial company in Australia. It is definitely doable. Some skeptics will say it's not. We can prove, and others here on the panel can prove that it is doable. Second lesson, you cannot do it alone. You have seen all the examples that were discussed before. you don't wait too long. So here, examples of, innovators here, Skykraft, you see Gilmore. Actually, are they launching the rocket right now? I think that was the time I heard. But there are a few other companies here. International company, you need to go out of Australia, obviously. Government, research, universities, skills, everything. So that's how you build a company and things together in Australia. And you will have heard this yesterday, space is like a team sport. So that's what it is. That's probably what I'm the most proud of, is building the team. And that's what we have here. And that will be my final slide for you, because I want to leave them in the spotlight. But that's the Neumann space team. And a lot of them are very young. Number of interns in there. Actually, we have one in the room. Sam somewhere. I don't see you, but yep, she's over there. That's the critical aspect, build that team. And we can do it in Australia. So yes, a lot of people will transition from other industries or come out of uni, but we're starting to see more and more of that. So we are leveraging this now and building critical mass. What's next for Neumann Space? Continue what we do best, continue the product development, continue the people, the team, building more collaboration. But now that we have customers, now it's time to scale. So that scaling aspect is manufacturing. So a number of companies, if you start talking with companies in Australia now, are really going from that, we're doing R&D and few in-orbit demonstration to, okay, how do we do manufacturing? How do we do, batch of product and start to export and learn about all this and international logistics and everything? It's quite interesting. And so it's a shift in what we do as leaders of companies like that. Certainly you have to move on and do all those things. We will announce soon our first employee in the US. And then, our target markets are US and Europe. So, we're already exporting to Europe. It's going to be okay. Or do we attack the US markets? We're looking at how do we manufacture there. Some companies are asking for local manufacturing. Also, to get ready for defense, we are doing that. It's growing, developing. Skykraft is another. Sorry, I'm talking a lot about Skykraft actually, but that's another example of stuff that can be done with defense. And finally, as we start to grow and scale, then we look at more strategic aspect, not just focusing on what your technology is, but what else we can do. And I think that's going to be very interesting in the next few years. So to finish on what we want to do, what we are going to do in the future, it's really accelerate. And I like the beginning and the end and the new beginning or something like that. For us, I think the last few years were about learning to walk, and we need to learn to run. That's what it is. Thank you.
Thank you very much, Herve. I also think it was, there's a great story, Herve, of one of the first times an Australian bit of space hardware was carried on board a commercial airliner in your luggage, right? Because you had no explosives, it was just a bit of electronics that could power a spacecraft.
Yes, and the most scary part recently was going through Sydney Airport, and they stopped me, which they do like 20% of the time. And the lady takes your suitcase, put it on the screen where she looks at stuff and talks to you. And she put it on the screen, she looks at me and she says, "It's a propulsion system, right?" And I'm like, "How do you know that?" I said, "Yeah, I've seen it before." And I was, yes. I was very happy.
Beautiful, fantastic. Now, speaking of fantastic, stratospheric. We're so delighted to have Jennifer here from Stratoship, who've been on quite an adventure. So I can't wait to hear all about the stories of this exciting company that's burst out of nowhere onto the scene. Take it away, Jennifer, please.
Thank you, Tim. So for those of you who haven't met me before, my name's Jennifer Williams. I'm the Chief Operating Officer at Stratoship. And for those of you who don't know us, we're building high-altitude airships. So that's an example of what it looks like. It's much shinier in person. And we're playing in the stratosphere around 18 to 20 kilometres high. We're using them primarily for persistent services, particularly in bushfire spotting and ignition detection. So on May the 5th, we launched at dawn and we made it up to the stratosphere, 65,000 feet. It took about an hour for us to reach the stratosphere, and once we were up there, we were only expecting the flight to last about 4 hours. But we lasted in the stratosphere for 8 hours, well beyond our expectations. The whole flight flew for 11 hours and 12 minutes, which was absolutely incredible. And in that flight, we marked Australia's first sovereign, designed, built, and flown HAPS, or high altitude platform, to make it to the stratosphere. Sorry. Thank you. And to back that up as well, we offered rideshare on that. So we have a payload bay that sits below the Stratoship, And we fully booked out on that launch mission. We had a mix of space payloads and stratospheric payloads, and people just wanting to test their technology and see what it would do in the stratosphere at a completely different altitude to anything that they've considered before. So I'm very, very proud of that as well. But why the stratosphere? Well, we know that we've got beautiful satellites rotating around the Earth, detecting hotspots and having a look at ignition already. But Australia is reliant on foreign satellites to do this at the moment. And if you have a look at the data, there's a lot of uncertainty about this. So this was actually one of the better random hotspots that I picked on this day. On Monday morning, I woke up in the morning and I grabbed this screenshot and I selected that hotspot that you can see there with the red arrow. You can see that there is accuracy of 400 or nearly 400 meters in any direction and 88% confidence, which is pretty good. We don't really know if the fire's there or not, but it also hadn't been detected for more than 8 hours. That's a long time for something to sit in a status of being unknown. At this point, I believe it was Terra had just flown overhead as I took this screenshot. And on that point in particular, especially in remote Australia, the next pass wasn't going to be until 12 hours away, well past the hottest point of the day. You know how much damage a fire can cause in that time, especially in Australia in this landscape. So we came across this problem in RMIT's Firefly Pathfinder Challenge, and we wanted to find a way to work past it. So we basically sought to try and find a better way to solve this issue. And we don't know, or emergency services don't know if they need to look after each of these hotspots or if they need to wait for them to burn out, or do they actually need to go out and send a team? Especially in remote areas, how do you prioritize your different resources when you've got so few people and so few resources? And so on top of this, I mentioned earlier that we rely on foreign satellites. There's 6 satellites available in this hotspots map. All of them are owned and operated by US, which is great because we're generally pretty friendly with US, but none of them are sovereign owned. And 5 of those 6 are well past their mission expiry date. That means we've really only got 1 satellite that we're actually genuinely able to rely on for this sort of data. So I love these images. They're great birthday presents. So how does emergency service prioritize this information? So RMIT wanted to look at this with their Firefly Pathfinder challenge. And we were part of that challenge. So we built this. This is called the Pebble. This was our very, very first stratospheric platform that we built. We flew it in 2021, and we made it up to the stratosphere. We managed to take these beautiful images with a very, very old GoPro that we strapped on board. So it was designed to not burst, unlike a traditional weather balloon, and so we could have a network of them that were constantly reusable, and we could continuously adapt them to complement this balloon network that RMIT were looking to have for constant bushfire detection. So after that point, RMIT realised that maybe balloons aren't the right way to go. Maybe this network needs to be something else. Balloons usually have a very, very short duration of about 4 to 6 hours. So what else can we build as a high altitude platform? So they came up with the HAPS challenge in conjunction with Air Warfare Centre and Trusted Autonomous Systems. They launched that challenge in 2022, and we built our full-scale first prototype in 2022 to fly. But you can see that HAPS, it's not always the easiest thing to build. Historically, other programs have spent anywhere up to $80 million just to develop one high-altitude platform, just to fly it once, watch it crash, and then never touch the programming again. We didn't have $80 million. So as you can see here, we were building the Stratoship on Dan's kitchen table, who's one of my co-founders. That's his daughter Lillian there in her school sports uniform, helping out in her spare time. And this is basically how we approached the entire production of this airship. We tried to pull everything off the shelf where we could find it. We were testing control systems at the local aircraft club because there's nowhere else that you can find a free paddock that you can just spin a little airship around in. And we were just trying to do everything as low cost as humanly possible. So the HAPS challenge required us to build an airship with a 7-day endurance, being able to hold 10 kilograms of payload, which is a massive ask of a little Australian company. But we did it, and this is what we built. This is the SZ155. It's our very first full-scale prototype. It's 25 meters long by 10 meters high. That's Dan for scale. We didn't have a banana handy. And so, yeah, and that's it, inflated during a test in the Brisbane Netball Centre. So it was one of 2 buildings in all of Brisbane that could actually accommodate the full scale of the Stratoship. The CASA application alone, because we all need approval to fly, don't we? And it's great being able to fly whenever we want to, but the CASA application alone took 11 months. So our biggest challenge wasn't just to build and manufacture this, it was also to make sure we had all the right approvals, processes, insurances, pilots and everything else to make sure that we were all above board and met all of the regulations that CASA asked of us. So we had flown this twice before in low altitude flights. We learned so much in both of those flights. It's not shown in this photo, but there's a structure that sits underneath that's semi-rigid. And one of the very first things we used, because we were looking for something that's thin, telescopic and semi-rigid to use, and what meets that definition? It would be a fishing rod. So we went out and we found 6-metre long fishing rods, which no one would ever, in their right mind, ever buy. But we found them and we used them, and they were awesome until we went to inflate with helium one day, and they snapped at the ends. They weren't strong enough. They weren't what we needed. So we found out a lot of lessons the hard way just by going out and testing it, as Patrick was stating, and just really putting it to the test. And that's why those 2 flights were really, really, really important to us beforehand, because without that we would have no idea what we were doing. So, and at dawn on May the 5th, we went out. This was taken basically on the back of a truck. We just had a trailer that we tied it down to as we filled it full of helium. And we launched shortly afterwards. It took an hour for us to get up to the stratosphere, up to 65,000 feet. And we stayed up there for those 8 hours. Yeah, so I'm still super, super impressed. You can see there that the vertical speed is still, that's in feet, just so people are aware. We're not going that fast, but that's still raising up, and we did actually go up to nearly 66,000 feet, which is a massive achievement. So I don't think I've actually shown this footage anywhere else before, but I'm really, really glad to be showing it here. So this was taken mostly during the flight. So that's on launch. You can see our propulsion control system at the bottom, so we do have the ability to propel it in the stratosphere, and that's it during a turn. So we really, really got to see what it could do. That's a view over central Queensland. We launched near Winton, about 85 kilometres outside of Winton. And that's it while it's relatively stationary and finished turning. So yeah, it was amazing to see these river systems. It was shortly after the floods went through North Queensland as well, so we got to see some really, really interesting data from that. So, and I'm also pleased to announce that we're flying again in late August. So only 6 weeks away from now, but the beauty of being able to own and develop your own system is that you do have the freedom to launch it again within CASA regulations, but we do have the ability to fly again whenever we want to. So we're going back out to central Queensland then and launching. We did actually, well, we're partnering with CSIRO, so on the next flight we are flying their hyperspectral payload. This is specifically for fire ignition and detection. This payload will be coming up with us at the end of August to put our system to the test to see if we can test ignitions in real time and make sure we can provide that data back to our emergency services, particularly over regional areas as well. So just with that one gimbal sensor alone, we can scan 1,500 square kilometres with one airship. So we're also partnering it with a thermal tester and RGB cameras as well to really be able to make sure that we're picking out the right data and sharing the appropriate information with those emergency services as we detect bushfires. And so, yeah, we've also already sold out of rideshare space on that next flight, which I'm also very proud of, and we're taking bookings for the next flight after them, which I don't have a date for yet, but if you're interested in testing your space, stratospheric or other payload, hit me up. We've got plenty of space coming up in future flights, and we do have the ability to fly almost any time from our location in central Queensland. So I'm around today and tonight for any questions, and thank you.
Thank you so much, Jennifer. That's so exciting. Look at that photograph. We're so proud of all of our teams today, and so excited to be talking to you about your achievements. Isn't it the coolest thing? Now, audience, this is a time for you. I'm going to lead off with a couple of questions, but we're also really keen to hear from you. And I'm not sure if we have like a roving mic, but anyway, what we're going to see, we're going to try and do our best. We have very bright lights on us, so we can hardly see anything of you, but there are people out there, guys. So first question I had, there's this old joke that it typically takes about 8 years to be an overnight success. I was curious, I was going to take a quick straw poll. Karla, you may not have this information, I'm not sure, but I happen to know, when it comes to HEO, that the guys were talking about imaging their first asteroid in around 2014. So that's been about 11 years to get going. David, how long have you been chatting about this mission or these missions in DSTG? Let's go down the road. Yeah.
Yeah, so with Buccaneer, we probably started talking about it, like there were some initial efforts, I would say around 2012, 2013, and those initial efforts stalled for one reason and another, but yeah, we really got momentum around 2015 when we partnered with the University of New South Wales, Canberra, and of course Craig was part of the university at that time. You know, COVID slowed things down after our first mission. COVID slowed things down a little bit, but we've regained our momentum now. So, you know, 10 years, yeah.
There you go, Patrick.
I'm also maybe not the right person to ask. I think you might know that
boy.
better.
Gosh, well, it's true. I guess we, Professor Eva Cairns and Professor Andrew Dempster, and I think Dr. Jason Held and a few other folks at that time, probably back around 2013, were thinking about doing a private space mission, and so it took about, I guess, another 10 years. Yeah, amazing.
Yeah, as you said, best knowledge of Will and Haranya's early days with HEO, but I think in the current context of non-Earth imagery, they really started getting into that in 2020 and started reaching out to different Earth observation providers and started figuring out whether this was possible. And yeah, 5 years later, we're here now with over 46 sensors and continuing to grow. Yeah.
Terrific. Thanks, Karla. So, Craig, going back to your first engagement, did you start thinking about what Skykraft became when you were doing that work with David back in the day?
Yeah, so Skykraft came out of the UNSW Canberra Space thing, and that stood up basically the start of 2014. So I actually remember I was at an oceanographic, we're kind of all polymaths, right? Which means we know nothing about a very wide range of subjects. But I was actually in an oceanographic engineering conference with Michael Frater in San Diego, and he actually had, he said, "Oh, I'll meet you at the bar a bit later. You know, we just have a chat."
Michael Frater, the CEO.
Michael Frater is now our CEO. At the time, he was rector at UNSW Canberra, so dean of faculty. But he actually was interviewing for the head of that group, and so he interviewed Professor Russell Boyce at October 2013 in San Diego, and then we'll talk about it at the bar afterwards. And that sort of kicked off the space group. At the same time, we also kicked off a cyber group in the university. And then, yeah, that sort of things have snowballed from there. And Michael didn't come across straight away as CEO. We actually had one of our sort of VC type funders that was offering to help us find a CEO, and we sort of weren't sure this was a good idea, so we got in first and appointed a CEO that we liked, rather than one that appointed by a VC. And that's worked out really well.
Now, Herve and Jennifer, you did a terrific job of talking about your journey, so I'll switch to a slightly different question, and then we might come back, which is inspired a little bit by Craig. The problem that you identified for the company, when you came across that personally, how did that resonate for you? So maybe starting with you, Jennifer, you were definitely driven by this problem, this issue, which I think is common with every single company. To what extent did that kind of get you through the tough times?
I think everybody, can I ask a question? Who here has known someone affected by bushfires? I'm seeing quite a few hands go up. We live in Australia. It's inherently the danger of living here. It's a great country, but we do suffer them every day. So, and I remember being near Canberra during the Black bushfire. It's something that's quite close to home for me. So I'm happy to get up every morning and know that that's going to save someone's life at the end of the day. I know it's going to bring another firefighter home safely. Like that's what I'm looking forward to. So,
Herve.
To be honest, for us, it's by the Neumann, our founder, who had that vision more than 10 years ago. And then when I joined, so this is actually cool. I was more interested in the tech and the change of building the company. But when you go into it, then it becomes your key driver every day, and you think about this every day. And what's interesting is to see the ecosystem develop and the need develop, understanding the value of your product, or you position it and everything. And so that, like, when we started to talk propulsion, that was before the FCC, the Federal Communication Commission, thank you, in the US started to say, hey, we really have a problem in space with so many satellites who are launching, we need to remove them. And they mandated to deorbit satellites within 5 years of the end of the mission. Before that, there was a guideline that was 25 years. And the closer to you are to Earth, the easier it is, the higher you are, the more difficult it is. So suddenly it's like, yeah, that makes even more sense, and then you keep pushing, so yeah.
So the debris problem is actually a big inspiration for you guys as well.
Absolutely, yeah, so we're talking, constellation, more and more satellites, so we need to have a sustainable solution for that, so we can keep doing that. But we have more and more debris. I mean, you were talking about debris monitoring, tracking, all those things. It is super important. So if you're not familiar, just Google Kessler syndrome. It's simply this idea that we have more and more objects in orbit. When we send an orbit, they're already there, and if there is a collision, that starts another one, and then all this could be destroyed. And if this happened, then you say no more bushfire detection, no more weather, no more GPS, no more. I mean, we go back, I don't know, 50 years, something like that. So it is something critical. So for us, we prove we can use debris as propellant with the US Space Force. So, which is also interesting, is to see what is here today as a market, what is the future. So an interesting thing with our system is we have a market today, like we're selling it today, but we're also part of those forward-thinking projects, stuff that seems a bit like science fiction maybe for people, like, hey, we can go and grab a satellite and recycle it and everything, but the technologies are actually there. It's a matter of building the infrastructure, putting this together, but it's there. So yeah, we're passionate about it.
That's great, and thank you, Herve. And I'm intrigued, Craig, your story about the aviation sector in particular that's kind of inspired you, and also this idea, well, there's an opportunity to do a better job with ADSB, but there's also a lot more we can do for aircraft. Do you have a connection to aviation? Is there something that I know that you guys partner very closely with Air Services Australia, who I understand are responsible for some really high fraction of global traffic management. What's that thing that gets you out of bed connected to that problem?
So yeah, I mean, I've been involved in aviation since I was 17 and left home to join the Air Force and went to ADFA, and then fixing aeroplanes was my first job, or actually looking after people that fixed aeroplanes was kind of the truth. I normally just let other people do the work and I claim the credit. But I guess the good thing about our service is that a lot of the money actually comes from the North Atlantic. So there's a big congestion problem over the North Atlantic where there's a lot of planes all want to fly between roughly the same city pairs, and there's not a lot of space for them to fly through. And of course, to be energy efficient, they want to fly at the correct altitude for their mass and type of engine they have, and that's a very narrow band. And then going forward, there's a problem with contrails as well, where it turns out aircraft contrails, if you make them in the morning, then they reflect a whole heap of sunlight and they become overall a net cooling effect on the Earth. And if you make them in the evening, they make a warm blanket, and over the entire life of the contrail, they become a net warming effect. So choosing when you make contrails is actually also very important. So it's a combination of fuel efficiency and contrails and whatever. But the whole idea is if you provide almost instant communication, it's a communication rather than a surveillance that actually dimensions it, which is why the Ariane proposition wasn't necessarily as good as what people thought, because it lets you see where the aircraft are, but you can't intervene quick enough, which means you can't space them that close together because you won't get the right safety margin. So that all flows. So that's where most of the money is. But most of the benefit is actually in the other low wealth density parts of the world. I always call it low wealth density because it includes Australia. But a lot of these places, you just have really low GDP per capita. And a lot of them don't have infrastructure, Pacific Islands, parts of Africa and all that sort of stuff where PNG, people are very dependent on aviation and actually don't have a lot of money. And so we can actually provide services cheaper than you can do it from terrestrial services. And so, in effect, I always describe charity. You want to give money out of your own pocket so you don't get greedy, but actually if you want to do good in the world, you're far better off to find a day job that actually pays its way, that does good in the world. Yeah, and so this one, like, you know, we're solving a greenhouse gas problem in Europe. This is great, and that pays for it. And then there's this side benefit that, you know, it's things you would do for free. You know, you go and have a global challenge, you know, to a bunch of school kids to do something good for the world. You get that for free on the side. It's really good.
Thank you so much, Craig. I feel I have a very different perspective on Skykraft and a richer one. Thank you. That was marvelous. And you are a polymath, I can tell. Okay, we're going to come up to the first couple of questions from the audience soon, but I just wanted to complete this. Karla, you graduated only a few years ago. You've had a few roles, and now you've landed on your feet in this exciting job. What gets you out of bed in the morning? What's exciting you right now?
So I graduated end of 2022 and I did a physics degree. I didn't know where I was going to go, but I ended up at an internship at Cicada Innovations at the Space Industry Hub where I met you, Tim, and Iwan Cornelius at Amentum Space started opening my eyes to all of the great companies here in Australia and realised that I could have a job in the space industry here. And then made my way over to HEO. So the thing that gets me out of bed in the morning, I get to look at space all day. That's pretty cool. I get to literally look at satellites. I open my laptop every morning. I do what we call hunting satellites. So that is a very cool job. But I think the thing that gets me out of bed is the future for HEO. We want to be everywhere and imaging everything, so that future is very exciting, and that's what gets me out of bed.
Fantastic. I had this vision of you strapping on these steampunk goggles, you know, to hunt the satellites on a Monday morning.
We make the joke at work that we're getting closer and closer to controlling a satellite with an Xbox controller. So.
It'll happen. I'm sure it'll happen. Patrick, all of you are sort of talking a lot about how well you're knowing your customers now. You know, you've got to know all of your payload customers. Do you feel? I feel like you're quite paternal towards them. These are your kids, almost, that you're looking after. Would that be true? Or they're just the paying customers, and they should shut up and take their voltage and be grateful?
No, yeah, you're right. We've worked very close with them together, grew close to all the guys, can really call nearly all of them very good friends of mine now, and looking after their payloads has been great for the last year. I was going to say that the satellites were kind of like my kids. They also keep you up at night because they only fly over twice a day, and one is midnight, and that's not really good for your sleep cycle, but it's been really good to connect with all these people and see all these companies that flew with us grow over the last. I mean, Waratah Seed we started as well 4 years ago now. To see the companies grow, and yes, some of them might not be necessarily working in the space sector anymore, but all their achievements with us led them to have other successes in other fields and talk to other big companies and go their own way.
How many times a day do you pull out the Waratah Seed website and refresh the page which shows it where the spacecraft is?
I don't really use that website. We do have it for everybody who's interested. There's a dashboard that shows where exactly our spacecraft are orbiting right now. One of our payload teams actually built it for us. And we also used to upload our telemetry there. We haven't done it in a while because we were too busy with other things. No, I just built myself a little app that puts all the passes whenever it comes over Australia into my calendar.
Very cool. I love that. That's a nerd out right there. That's fantastic. David, lucky last, before we get your questions, folks.
Yeah, so, look, it's just really cool operating satellites. So just going through that whole cycle of concept and then design, build, test, operate is really, really cool. And you do become emotionally attached to the satellite. So with our first satellite, the risk mitigation mission CubeSat, that launched in 2017 and we operated in 2018. When it got to 1 year in orbit, we did have a birthday party for it. So we went to the park and someone made a cake, and so we celebrated its birthday. It lasted a year in orbit, And so we were pretty happy with that outcome. In not just fairly recently, it dived back into the atmosphere and burnt up, and there was a bit of a sense of sadness there. You know, our baby had died. But look, really, yeah, I guess it's just a lot of satisfaction on a number of fronts. So in terms of the payloads that we're experimenting with, just thinking about how they're beneficial for Australian defence and beneficial for the ecosystem. So a good example is the laser communications. It's much more secure. It has a very high bandwidth. So, you know, if it can be used in conjunction with what's typically been used in the past, which is radio frequency communications, you know, the two complement each other really well. So we see ourselves on that path of understanding, you know, new and different ways in which to communicate between space and ground, taking advantage of the, you know, the strengths of RF communications and optical communications, and just seeing those collaborative frameworks just grow and develop. So we got with our laser communications payload, we got a laser transmitter from the Aerospace Corporation in the US through an international collaboration. So that got us going there. And then DSTG collaborated with a number of universities, University of South Australia, of Western Australia, and Curtin University to develop the capability for the optical communications on Buccaneer. So we're sort of just one thing building on another, and a sort of collaborative network developing, which includes international collaboration as well through that MOU I mentioned, the way in which we got the laser transmitter. So this big web of collaborative enterprise developing just from a small beginning. It's very satisfying to see that and to see the Australian ecosystem involved in it. And also for my team, you know, just seeing all these young, I'm definitely the oldest by a long way person in the team. So just seeing the young people, you know, doing such a wonderful job progressing the mission, seeing them developing in their knowledge and understanding and their capability, and knowing that they will, for a long time, long after I'm retired, they'll be part of the space system here in Australia, the space ecosystem. That's very gratifying as well.
Fantastic. I've always visualised them wearing pirate hats and having cutlasses, you know, being the Buccaneer group. Okay, so I'm going to squint out into the audience, and who has a burning question they would like to ask our panel? You've been very patient and thoughtful, and I can't see very well at all, so very left. Okay.
Thank you. Hi, Sander Vos here from CSIRO. I might be playing the devil's advocate with this question, and it's for you, Craig. You mentioned you tailored your system to fit these existing aging systems in planes, right? Do you think that could be a strategic risk as well, as that starts to phase out to different systems, and what sort of role does Skykraft play then?
Yeah, so absolutely. I guess the insight on this is that for those who understand radio, aviation still use double sideband large carrier AM. It's the thing you used to tune to on your wireless in your car back, you know, in the 1970s, and it's a waveform from I think 1904. And nobody in their right mind in the world still uses it, but they persist. And the reason is they've kind of got this legacy attitude to life. Where it was good enough in the past, we understand it, and cutting over to a new system is really hard because they would have to support the old aircraft for 20 or 25, 30 years. My first job out of the Air Force, I was a dirty contractor, and I came in to do navigation warfare, but part of it was also going and looking at the impact of reduced vertical separation minima and a couple of other things, some tighter tolerances on navigation, a couple of other things on military platforms. And of course, yeah, we had all these things like F-111s and stuff were still around, and you went, we've got no interest in updating the avionics on these for the 3 times they're ever going to go to Europe in the rest of their life. And so you kind of went, actually, we're just going to legacy it through, and we'll just fly at the wrong altitude and talk to military UHF and whatever if we need to. So in effect, there's a lot of inertia there. You're quite right, eventually things will move on. But if I take a note out of David's book, I'll be long retired by then. Yeah, like I wish it was faster, but in some ways they're not wrong. It is frustrating, and I pull my hair out all the time at these ICAO forums going, really guys, what are we doing? But yeah, so it is a strategic risk, but it's one that I'm actually comfortable with, because the smart way to do this is to totally replace all the radios, but it's just not practical.
Thanks.
Thank you very much. We'll maybe go across across the room. And you can also yell at me, I'm next. Thank you.
Who was up next, sorry?
No. Did someone else have a question? No.
Thanks. Ben Hennessy from Raytheon Australia. Previous life, I had a background in air traffic control. So your CubeSat, is it a repeater or has it got a downlink?
Sorry, I assume that's for me. The only CubeSats we ever built were in conjunction with David and co. So Doug, Simon and I, that are all key people in Skykraft, we all swore that we were never going to build another CubeSat, having built them at UNSW. So the smallest satellite we've ever flown at Skykraft is over 100 litres. CubeSats are like 3, 6, 9 litres. So they're bigger than this table. And it's not a repeater, it's totally regenerative. So you've got digital data links, you're up from the ground, hop across multiple satellites, and then make a message on VHF, send it down to the aircraft, and then likewise on reverse. We actually listen to every radio channel in the entire aviation VHF band. There's only 400 channels, it's not that bad. And then when we detect traffic on them, we forward the relevant ones back down in real time to air traffic control. So you're dealing with latencies of like 30, 40 milliseconds in addition to anything that's in the voice switch. The voice switch, if you're in air traffic, the voice switch will often add somewhere close to 100 milliseconds worth of delay to the conversation, but it's still better than a geostationary type voice thing, so that works. But yeah, they're not CubeSats, they're medium-sized satellites, 100 to 200 litres each.
I think that's JJ.
Yeah, I know, Tim. You knew I'd be asking a question like this. So, if money was not the issue, we've got companies back in the States that are building whole rockets, 10 per year. If we're talking about scale, and that's what we want here, how are you building up to 10, 20, however many units, missions per year looking forward for your companies?
I can start with that one because we are doing a launch platform of our own. So at the moment, the Stratoship you saw, that was hand built. Half the fingerprints belong to Dan and half the fingerprints still belong to his daughter, and it took a very, very long time to put together. But the great thing is that now that we've done that, now we know how to make it faster and better, and we're coming up with, we're trying to find new material suppliers and things like that to be able to bring a lot of that production to Australia. So we source the material from the United States at the moment. It's got such a long lead time, and United States is tricky at the moment, so we're trying to do as much as we possibly can in Australia. So if money was no object, we would look to increase it. At the moment, we're sharing a co-working space up at Arm Hub in Brisbane. They've given us quite a large manufacturing space, but it's not big enough to build our second generation. That one was 25 metres. Our next one we're looking at probably about 40 to 50 metres long. We want a bigger warehouse, a lot more people. We want the option to be able to, the kind of people that we've been engaging have been people like seamstresses and people with experience with windsurfing because the masts are particularly strong and stable. So so we just want to be able to make sure that network, and we can bring all those interdisciplinary skills together into one building to be able to manufacture. Probably looking at 1 to 2 a week, and we're hoping that HAPS can become as common as normal planes are today, and we can take off at any point in time. So that's it for us. And the next Stratoship as well, we want to have an endurance of 2 months, and so we'd also have to have teams to go out and support that as well. So.
Yeah, look, it's a great question. I was talking before, like we're looking at ourselves and say, okay, we're going to send so many next year and the year after, and we're thinking we might be one of the, if not the Australian company that has most hardware in space, not by mass, but by number of units pretty soon. We build manufacturing capability where we say, all right, we can do for our CubeSat form factor 1 per day with no issue in 1 shift. We talk to Constellation customers at the moment, they do 100, 150, but we're talking to small sat, they're talking 1,000 units. So if you replenish this for 4 or 5 years, then you can do the math. So yeah, we were talking with defense earlier this week, and they're like, can you do full automation manufacturing? So because we have a quite big advantage from a manufacturing perspective with our system, like yes, that's the future. So we will be able to serve the market.
I'll go next. So I talked about coverage in a little kind of demo there, but HEO mission is to make space transparent, so that means having coverage at multiple orbits. I wouldn't say that if we had unlimited money we would launch our own satellites, because that's not what our mission is. We do not want to put things in space and create more, congestion than there already is. So continue to work with people that are already going up to space. We're big on dual use technologies, using satellites during their downtime, and yeah, just get all the way out to GEO. That's where we're kind of heading soon. And then I think the next big one is talent, and we're a startup. There's other startups here on the panel, and everyone works very hard and has to wear a lot of hats. So bolstering out and growing the space industry here in Australia. There's, as you said, a huge amount of talent here, and people are coming out of university and are really eager to work in the industry, but there maybe isn't enough jobs. So creating those jobs would be a great thing. Yeah.
So can I, before we move on, I'll just back up what Jennifer said. When you're talking about seamstresses and stuff like that, our satellite assembly, again, we're sort of, we set out to recruit bike mechanics, and it turned out we didn't need somebody so overqualified. It's kind of like, there's a bunch of jobs out there, and the beauty of this is that when you're dealing with a lot of systems, you can automate, and you do automate to a large extent. We use a lot of pick and place and stuff like that, again, with contract manufacturing. But the actual assembly, most of the time, the value add is so high that you don't care whether there's a week or two of labour in it, of women or manpower in it, because you're not that price sensitive, if that sort of makes sense. Like, you're dealing with something that's hundreds of thousands of dollars. A week or two salary isn't really worth optimising. You'll get around to it eventually, but you don't need to delete the labour, which actually means it's really quite good from a human point of view. So I'd back up, seamstresses and all that sort of stuff. This is exactly the sort of people that are coming into the industry. They're not all university graduates.
For us it would be building more spacecraft, the opposite of what T is trying to do, and really supporting more startups from all over Australia to get their first flight into space, or we could also launch more of HEO's payloads and something like that, and somebody else who has payloads, just to support them through the whole journey. And at that point, again, growing talent, from a university standpoint, being able to do educational outreach and those sort of things would be very good for us.
Terrific. Okay, we've got about 3 minutes to go, so we've probably got enough time for one question, and then we all need to probably have a stretch. Any last question that we can spot? I can use the power of the awkward silence. Terrific.
Thank you. Yeah, sorry, me again. There's just so many interesting things there on stage. Patrick, you mentioned one of the lessons learned was redundancy, right? You said you wanted to include redundancy in future missions. And redundancy sounds like an easy solution to improve reliability and lifetime, right? But it can be a very complex solution as well that can introduce risk and unknown other failure factors as well. How do you deal with that complexity and make those trade-offs?
That's a very good question. We have the experience now from Quawa 1 and Quawa 2 and Waratah Seed 1 from our 3 spacecraft that we launched, or at least for me that I launched. Eva has launched a couple more before. And we've seen how we had some redundancy on our OBC, on our onboard computer, but we had still a couple of systems that were single point failures. And we just want to improve on that in a way that even if we had that failure, we want to be able to recover from that as well. We're going to look at all the risks that are coming in through that. The main failures we've actually seen on our spacecraft was really just the South Atlantic anomaly. The radiation there is so incredibly strong, it's mental. So to be able to mitigate those and basically reboot just as it was before, that is the plan at this point.
Yeah, thank you. Yeah, I suppose we often think radiation is important, but it's difficult to sort of know really how important, so we just go and send some things up and we think it'll be fine. And then we realize for most part it is fine, but sometimes it's not. And I guess ensuring that we have systems that don't catastrophically fail in those events, is important. Thanks.
Yeah, exactly. Thanks.
Just speaking from our experience as well, we've found a lot of systems that require redundancy we can actually separate out into separate problems. And so you could build one system with 5 different layers of redundancy in it, or you could build 5 different systems with 1 layer of redundancy in it. And it just, the more you can separate out each problem, the more you can address every problem better, I think. And that's what we've learned a lot from doing our flight tests. So.
Yeah, but one thing we have seen also is you have different level of assets and different critical system or satellites, and so sometimes the customer will say, that's good enough for me for a price point, and I manage that redundancy at the constellation level. So I'll send more satellites if I have to, but keeping the cost down. So it's a balance, I guess.
I was just going to say too, and you may not want the we may not want the satellite to last 20 years, as I think we were discussing in one of the other sessions or previously, because we want to be able to refresh the technology. So it's getting that sweet spot. We want it to last long enough so that that's an effective use of money. But, and of course we can refresh by uplinking new firmware and that sort of thing, but at some point we want to refresh the hardware as well and make use of the the most modern technology. So it's a bit of a trade-off. Cost, of course, is very important in Australia. So in fact we have talking of radiation, the South Atlantic anomaly is definitely an difficulty for us as well. We've experienced quite a few single event upsets over the South Atlantic anomaly. So, but we have a one of my team members is doing a PhD at the University of South Australia, seeking to understand how we can, detect those dangerous radiation events and engage in self-protection within the satellite. So there's, that part of it as well, an interesting research area.
Thank you, everybody. We're run a little bit over time, but I hope that you've had a chance to get a sense of the incredible craft that you learn when you do stuff and you build on failures and you build on learnings and then you achieve some amazing things. So please join me in thanking our amazing panelists and the teams behind them for their achievements and your attention today. Thank you, everybody.